we're going to start talking about energy and how cells use energy, how cells generate energy from our food. We've used the term energy a few times now already this semester. We've talked about potential energy being stored in the chemical bonds, in particular in the covalent bonds. We've talked about energy being required for active transport of materials in and out of the cell. Now we're going to talk a little bit more specifically about what we mean by energy, and we're going to start to talk about how we produce ATP via cellular respiration. So energy and metabolism is going to be this topic. It's going to be a lot of definitions that aren't really applied yet, but in the next lecture on cell respiration we'll apply most of these terms. So this lecture is a little bit dry in that it's just really a lot of definitions. I'll just warn you of that now. We hear metabolism used a lot, and oftentimes this term is very misused. Metabolism is really the sum of all chemical reactions that take place in the body. So metabolism is really more accurately defined as the sum of all chemical reactions in a living organism. You hear people talk about, I have a slow metabolism, or I have a fast metabolism. In that context, they're kind of misusing that word. This is what it really means. And we can really divide metabolic reactions into two categories. We have what are called catabolic reactions, and we have what are called anabolic reactions. Catabolic reactions are going to be breaking things apart, and anabolic are going to be putting things together. So catabolic, this is going to be breaking molecules apart. And anabolic, this is going to be putting molecules together. In other words, just using AB as our molecule, catabolic would be taking A bonded to B and breaking that back down into A plus B. Anabolic is going to be the opposite. Anabolic is going to be taking A plus B and putting those together to form molecule AB. One of these is going to require energy, and one is going to release energy. And I think the best example of this is just thinking of, does it take energy to put something together? If you go to IKEA and you buy a dresser that's not put together versus buying one already assembled, that takes a lot of energy to put that together. So putting things together is going to require energy input. Anabolic reactions require energy input. Catabolic reactions, on the other hand, breaking things apart, that's going to release energy. So energy is very much tied to these metabolic reactions in the body. We also have this other term that's important to understand, and that is biochemical pathways. Under this heading of metabolism, we have some really important biochemical pathways. They're also called metabolic pathways. These are chemical reactions that don't just take place in one step. They're going to require multiple steps, and at each point there's an intermediate product that's significant. Cell respiration and photosynthesis are both really good examples of this. So these are multi-step chemical reactions. And at each step we're going to have a product that then breaks down and becomes something else, or a product that is being assembled and becomes something else. Again, two good examples of this are cellular respiration, which we're going to talk about in a lot of detail in the next unit, and photosynthesis. Both require multiple steps to get to those end products. So when we write the general formula for cellular respiration, which we've written a lot of times now, Remember, the general formula for cellular respiration is glucose plus oxygen breaking down to form carbon dioxide and water, and then ultimately 36 to 38 ATP. But this arrow is misleading because in this general formula we just draw one arrow. This would really be a lot of arrows. It's going to take a lot of steps to finally get to carbon dioxide and water, not just one step as implied by this arrow. Cell respiration is a metabolic pathway. It's a biochemical pathway. Multiple steps required. So again, a lot of definitions in this lecture. So this is an example of that. So you start with your initial reactant. By the way, another name for a reactant is a substrate. That's going to be a really important term when we start talking about enzymes. A reactant in a chemical reaction, when there's an enzyme involved, is called a substrate. So in reactions which require enzymes, which are most reactions in the body, that reactant is actually called a substrate. So you can see all these intermediates in this multi-step reaction until we finally get to the end product. Now we need to really start thinking about the flow of energy in systems. And obviously, food chains are significant in this story, and also chemistry, chemical bonds, and laws of physics are important in this story as well, because cells are really governed by the laws of physics and chemistry. So it might seem like things like laws of thermodynamics aren't really applicable to biology, but they're very much applicable to biology. I can't say that word for some reason. It's important to know that there are two forms of energy. There's what's called kinetic energy, and there's what's called potential energy. We've already talked about this term, potential energy. This is stored energy. And remember, we've talked about a major source of that being covalent bonds, especially the covalent bonds of our food molecules, as a really good example of potential energy. Kinetic energy is a little bit harder to understand. Kinetic energy is energy in motion. That's energy being used. And this is a good example of that. So potential energy, she has a lot of potential energy at the top of the slide. In fact, she has a lot more potential energy at the top of the slide than she does when she's at the bottom of the slide. And she was laying on the ground, not as much potential energy. Top of the slide, she's getting ready to fall down the slide. While she's actually in motion, that's kinetic energy. So kinetic energy is really energy in motion, energy being used. That's kinetic energy. But while it's still stored, it's just potential energy. And major source of that, covalent bonds. We get a lot of energy from the sun, and it's a very important part of the food chain, because remember that photosynthesis is really going to be the opposite of this. Rather than rewriting this equation, I'm just going to show it going this way. Remember, photosynthesis is taking carbon dioxide and water, and with the help of energy from the sun, we're going to store that energy from the sun in the covalent bonds of that glucose molecule. Now this glucose is a huge source of potential energy for other organisms. So all organisms on Earth really depend on this reaction of photosynthesis to generate chemical energy for the rest of the food chain. It's taking light energy from the sun and converting it to chemical energy that the whole rest of the food chain can use. That's pretty amazing. Laws of thermodynamics. I know we're covering a lot of different topics in quick succession here, but these definitions are all really important to know. There are two major laws of thermodynamics that you need to know about. And they really all involve the fact that energy is not created or destroyed, it just changes form. And it's going to change from an orderly form to a disorderly form as we use it. So this first law of thermodynamics, this is kind of wordy, but it says all of that. It says energy cannot be created or destroyed. Energy can only change from one form to another. and the total amount of energy in the universe remains constant. We can't create new energy, we can't destroy energy, and in each conversion, some energy is lost as heat. It's not really lost, but what happens is it becomes disorderly. So you put a log on the fire, that's a very organized, orderly form of energy. It's all packed in the covalent bonds of those molecules in that log. Now you light it, oxygen's present, you're going to combust, you're going to start breaking those bonds and releasing that energy. It's released as heat. We can't then just take that heat energy and repackage it as a log again. It doesn't happen that way. You also can't take that heat and now convert it to light energy. I'm pointing to something that doesn't exist there anymore. You can't convert it to light energy and have that be packaged in covalent bonds of our food molecules again. Once that energy is lost as heat, it's disorderly. So first law of thermodynamics. In its most simple terms, energy cannot be created or destroyed. It just changes form. Okay, and then the second law of thermodynamics involves this orderly form of energy becoming disorderly. As we use energy, it usually converts from an orderly state to a disorderly state. So second law of thermodynamics. Energy transformation converts matter from a more ordered form to a less ordered form. That disorder is called entropy. So really what the second law of thermodynamics is saying is entropy increases. Entropy is disorder. Entropy increases as energy is used. It's going to change from an orderly form to a disorderly form. I love this example. I can very much relate to this example at my house. Order very quickly turns to disorder. And once it becomes disorderly, it's almost impossible to get it back to this. It's certainly not going to happen all on its own. In fact, unless I do it, it's usually not going to happen at all. But this disorder happens seemingly spontaneously. It's almost like the second my child walks in the door, this happens. But this is a really good example of order versus disorder. And that's what happens with energy as we use it. The disorder is called entropy. Again, a lot of definitions. But these two come into play in understanding cell respiration and how the cell uses energy. These are two very important concepts when understanding the two different categories of chemical reaction. And it's not on this slide, but I want to tie it back to what we just talked about a few minutes ago for catabolic versus anabolic reactions. So remember, catabolic reactions are going to break things apart. So this is going to be AB breaking down into A plus B. And remember I said this releases energy. Okay, so that was catabolic. Then we had anabolic, which was putting things together. So anabolic reactions, that's going to be A plus B becoming AB. And remember, energy input is required. And now that energy that we put into this anabolic reaction is stored in that bond. So this becomes potential energy. Whatever energy we put in is now stored in that bond. When I said we released energy, this is the energy we released. It was the energy from that bond, from that covalent bond. So we can classify reactions this way in terms of putting things together or breaking things apart, requiring energy versus releasing energy. And then there are other terms associated with that as well. And that part of the story has to do with whether the reactants have more energy than the products or the other way around. So let's think about this. In this reaction, this catabolic reaction, we have this molecule, AB. It has a lot of energy in that bond. Once we break that bond and we release it, now we have A plus B. So this would be the reactants on this side of the arrow, and then the products would be on this side of the arrow. What do you think has more energy in this situation, the reactants or the products? The reactants are going to have more energy. This is where that energy is stored. So AB, when it's together, has a lot more energy than the separate A plus B. So in this type of reaction, the reactants have considerably more energy than the products. So reactants have more energy than the products. That molecule, before that bond is broken, has a lot more energy than the separate A plus B. And that's how energy is released. In fact, the amount of energy released is equal to the difference between those two. The amount of energy released from this reaction equals the difference between the energy contained in those reactants and the energy contained in those products. So this is the amount of energy released. And when a reaction releases energy, it's called an exergonic reaction. Energy release. I like to think of it as energy is exiting the system. Exergonic. This whole story is tied together. Breaking things apart, reactants having more energy than the product, energy being released. All those terms go together. Let's look at this scenario. Putting things together. So let's think about what has more energy in this situation, the reactants or the products. These are our reactants, and these are our products. We had to put energy in to get to the products. So it makes sense that the products would have more energy. It's like putting money in the bank. You start off with this balance, and we're going to go up to that balance. Also, we know that we had to put energy in, and now that potential energy is contained in that bond. So it makes sense that in this scenario, the reactants actually have a lot less energy than the products. So looking at energy in the reactants versus the products, in an anabolic reaction, reactants have less energy than the products. So reactants have less energy than the products. Energy input is required, and the amount of energy input that's required, again, is equal to the difference between the two. So this is the amount of energy input that's going to be required. The difference in energy between the reactants and the products. Again, that makes sense. Bank balance. If this is your starting balance, and this is your ending balance, this is how much money you had to input to get to that balance. Same thing for energy. When energy input is required, because the products have more energy, that is called an endergonic reaction. So exergonic and endergonic. So all of this story goes together. Anabolic, endergonic, energy input required. Reactants have less energy than the products. These are very important terms to understand. Let's think about photosynthesis versus cellular respiration. Okay, in cell respiration, Remember, we're taking carbon dioxide and water. I'm sorry, let me start all over with that. In cell respiration, we're taking glucose and oxygen, and we're breaking that down to produce carbon dioxide and water. Breaking things down. Catabolic. Releasing energy. That would be this scenario. So a good example of a catabolic exergonic reaction is going to be cell respiration. Cell respiration is an exergonic energy releasing reaction. Remember, that's the whole point of cell respiration. Break the bonds of our food molecules, release that energy, and package it as ATP. Endergonic is going to be photosynthesis. Remember, in photosynthesis, we're going to go the opposite direction. We know that glucose has a lot more energy than carbon dioxide and water. We're going to take energy input from the sun to produce that glucose from carbon dioxide and water. So photosynthesis is endergonic. Photosynthesis is an excellent example of an endergonic reaction.